good insights about the technology that Ashok sir is going to be explained. So Ashok sir, the podium is all yours. You can take charge over from here, and you can start the session, sir.
Thank you, Ashish sir. Once again, a very good afternoon to all of you, all the participants. So there are 160 plus have joined. Okay, then I think we can start. Okay. Yes, let me share the screen. Yes. Okay, I think my screen is visible. Fine. So
Yes, sir. Screen is properly visible, and you are quite good audible.
yes.
Yeah.
Okay, so let me revise things where we left off yesterday, right? So in that way, it would be easier to get connected. Okay. So 1 minute, huh? Right. Yes. Fine. Yes. Okay. This is the point where we left off yesterday. Let me enlarge a bit. Okay. These are the things which we discussed yesterday, right? Okay. So basically, like again, the motivation is we need to do the hardware analysis of quantum computers. Okay, so that we could like we can come up with a better hardware, quantum hardware. Fine. Okay, so I hope the screen is sufficient. I think. Do you want me to go with full screen? I think full screen is slightly. Maybe full screen for the time being. Yeah, right. Escape is there. Okay, so the canonical ensemble means I would use the system of particles, right? Microscopic, put together, create a macroscopic, and allow this macroscopic system to interact with the surrounding, let's say environment. In that case, what happens to the system? If I know, right, thermodynamically or statistically, if I know, then I am through. I can just do any understanding of qubits being exposed to the environment. Okay, right? So here, yesterday we discussed that I can call the system which I'm considering as a system A, and if it is in connection with the environment, let me call that environment as A prime, right? Overall combined system would be A plus A prime. Now, because of the interaction with the systems with the surrounding, what happens? I'm sorry. The system could get rearranged different fashion because there are so many internal constituents in the system. They can get rearranged, and the rearrangement is not one fixed rearrangement. They can do several ways of rearrangement. Once they try to rearrange, they may constitute some energy, slightly change another energy. If the reservoir is allowed to interact with the surrounding environment, it can have certain range of energies, but not infinite number of energy, certain range of energies. That is what showed here, E to E plus delta E. Okay, right? So in this case, if I have to count, right, if I have to count how many number of such states available for the system, those states are called accessible states to the system. Okay. Now the question is, what is the chance of system falling into a particular accessible state if I want to ask? So then I can find the probability with which the system would exist with the energy correspond to ER, where probability would be some probability if ER falls within E to E plus delta E, that is delta E range window, small window. Otherwise, we can say probability is 0. Now, if the system is not interacting with the environment, in that case, it has to got its own energy, its own rearrangement. Okay. In that case, every possible rearrangement state is equally likely as per the thermodynamics. Okay. Right. So now, let's say when the system is interacting with the environment, in that case, I can talk in terms of overall energy of the system. Okay, which would be the system plus the environment. Okay, where environment, let me call it as a prime, which is much larger than the system itself, where definitely there will be some change in the environment, but not much, because if I just take a glass of hot water, put it in my table in this my cabin, what is the effect of hot water to the cabin would be very minute. It's not much. Okay, fine. So but there will be effect, but negligible effect. But when it comes to system, a serious amount of effect will be there as the glass cools down with the temperature. Similarly, the arrangement of water particles also gets rearranged. Okay, now if I talk in terms of how many number of states available for this particles in a glass, right, that will be connected to the overall energy around and internal energy. So that is what I was showing here. Er plus E prime is equal to E0. E is total energy of the system, entire system. Er is the part of system which is I'm considering, and E prime is environment. So reservoir energy usually would be E0, right? E0, 0 stands for the moment I just brought the two systems into contact, immediate point. As time progress, 0 would go to 1 and so on, higher values. So that is what I meant. Okay. Now, if I have to count how many number of accessible states are available for the system to exist in, that I would say some omega prime. Okay, omega prime is just the number of states I would be counting. What is the exact form of this omega prime? We will definitely find it out. We found yesterday. Okay, so omega prime, which is a function of E naught minus ER. Okay, so it's a directly proportionality. PR is directly proportional. So I can write some proportionality constant C prime. Later we can find, because the sum of all the probabilities should sum to 1. So I use that and I can get C prime. One thing I just notice here is ER is much smaller than E. Okay, so that is the case. I can expand this number of accessible states omega prime about E is equal to E naught. Okay, means overall the overall energy around E naught, or the E prime, the reservoir energy, is equal to E naught. At that point, here you see, I can expand, and since this is a function which is increasing rapidly, because it's a huge number of states are accessible, so I make it smaller, slowly varying by putting a log, and then I can expand that. Once I see the higher order terms gets negligible. Okay, right? Higher order terms are negligible because they are actually order of ER, higher order powers. So higher order terms are negligible, and the derivative what I have here, I can just approximate as 1 over Boltzmann constant into T. That is a beta. Okay, why I am just approximating? If you just see the dimensions of the system, which would be 1 over energy. So I will approximate that as a thermal energy, because the thermal energy coming from reservoir to the system, which is inducing changes in the system. So I will put that. The moment I put that, my x like omega, which omega prime would become a function of omega prime at E naught exponential minus beta ER. Okay, so this is what we get. The moment I got what is a omega prime, the number of accessible states for the system, for the overall system, if I get, it becomes straightforward to find what is the probability of the system to take a particular value. Okay, so what is given in this rectangular box is that. So that is very, very important. So the probability, you can do a lot of things. You can find what is the mean energy and so on, other things are there. So the most important part is what is there in the denominator. It is called a partition function. Okay, right? So the PR, what I have got in the previous case, it is actually distribution of the entire system accessible states. Okay, so if you carefully notice within a PR, the numerator, if you within a PR, if you notice, okay, let's see here. Fine. Okay, where is that? Yeah. What you see is PR is actually a function of number of accessible states and also the exponential function. So the number of accessible states is increasing function, exponential function is decreasing. So together they create some kind of a peak where it will peak at the average value of energy. Okay, right? So just to understand this probability distribution for a simple macroscopic system to macroscopic system conversion, we took a paramagnetic setup where electron, if I just take electron or atom, which can arrange in up spin or a down spin, let's say it has two ways, up and down only. In that case, if it acquires an energy, magnetic energy of E plus E minus, okay, for external magnetic field H, when it is applied, magnetic energy is acquired is this. So in that case, what is the chance of system to be existing in either plus state or up state or down state? You can easily calculate. The moment you calculate, you can find a mean magnetic moment. Okay, and if I have a mean magnetic moment, I can also find mean magnetization of the system, the paramagnetic system. So interestingly, magnetization with respect to applied field is initially increasing and later on it is just saturates. Okay, so H and T are the temperatures are very, very interesting and important factors here. As temperature increases, the magnetization would not be there at all. Okay, right? So that is what we saw yesterday. Fine. And the mean values in general, if I want to calculate, how do I calculate? Okay, so if I know the PR, easily you can calculate the mean value, let's say mean energy in this particular case, okay, where I just take the summation of energies multiplied by probability. Probability is there. Okay, so if you carefully see this entire expression, I can do some kind of a mathematical jugglery, some trick I can play. What is the trick is, just to take the numerator. If I just take a derivative of the numerator with a beta, I would get, okay, I would get the denominator. Sorry, you take the denominator, take the derivative of the denominator with the beta, I'll get the numerator. Okay, so I just use that trick to represent E, the average energy, E bar. Sometimes I write left angle and right angle, that is also acceptable. If I write E bar, okay, is equal to minus partial derivative of log Z with respect to beta. If I do that, I would get average energy of the system. Okay, right? So what is the power of partition function? The Z we can just even see here. What is that is, as you know, Z is a function of X and beta. Z is function of X and beta. Okay, In fact, Z is a function of beta and Z is function of ER. ER is a function of X, so Z would become function of X and beta. X is a position here. So what I will do, any change in Z would be partial change in Z with respect to X multiplied by some change in X plus partial change in ln Z with respect to beta multiplied by d beta. This is I have, okay. Now I can use some thermodynamics laws, that is energy change with respect to position is actually force into displacement is work done. So if the external environment created some work done within the system with rearrangement, so that I can say the internal work done. Whatever heat supplied is used for internal work done and also hiking the energy of the system. Okay, so that is the thermodynamics laws. Okay, from there I can find what is the average work done within the system. Let's say different locations, there may be different energies. So you can do that and you can find the connection between the partition function as well as the average energy as well as order in the system, that is the entropy. Okay, we derived that. Entropy usually increases with the amount of heat is added. Suppose I gave an example day before yesterday. If I have a classroom with a nicely seated student, orderly, if I close the entire door, increase the temperature, students will go haphazardly. That is increasing the disorder with the increase in the temperature. That is what usually happens. If you take a glass of hot water, increase the temperature, they haphazardly move around. So that is what increase in the entropy. That is actually connected to the partition function, to the average energy. So the moment if I know partition function, you can find average energy and also you can find the entropy of the system. So this is all internally interconnected. So so when I say partition, sorry, entropy is connected to the probabilities also, probability of particular existence of a particular system with particular energy. So even that derivation also I have given in the last class when I have ln z known. Okay, and let me go further. And if I just take a system, for example, a spring mass system where kinetic energy is p square by 2m, potential energy is half kx square. Please don't confuse with the k. Here k is a spring constant in the system and k I use so far is a Boltzmann constant. Let me put k naught for the spring constant. So in this case, if you see, energy is quadratically depending on position and momentum. If there is any system of such dependency on the coordinates or the dimensions of the dimensions which describe the system, if that case is there, okay, so every coordinate which is quadratically contributing to the energy would contribute energy of thermal energy equal to half k T, where k is a Boltzmann constant. Doesn't matter, I don't need to bother any what is it's getting multiplied and all. I can simply say it is contributes with a thermal energy, okay, of half kt. It is called a equipartition theorem. Okay, we discussed that also. Let me see, there is a chat message. Please tell again the title of the book. The book is the book name is the thermal statistical physics and statistical and thermal physics are the fundamentals of statistical and thermal physics by Reef, R-I-E-F. Correct, the name is absolutely right. Okay, I guess I have showed you earlier the book title. I'll show it once again at the end of the class today. Okay, so the equipartition theorem says the contribution from the kinetic energy is half kT, contribution from the potential energy is half kT. So I don't need to bother anything about what is involved in kinetic and potential energy. Simply I can add two half kTs, that will give me kT. That is what the equipartition theorem says. And we discussed the proof also from knowing the distribution of the system. Okay, see here we got half kT for each case. Fine. Now how this is connected, how this equipartition theorem is connected to the real world. For example, in the classical limit, the classical limit means all the electrons, I don't bother about electrons whether distinguishable, they are indistinguishable anyway. I don't bother about where they're located. They may be in a combined band of locations. Okay, let's say if I reduce the temperature of the system to very, very low values, in that case, okay, kT would be very small, and the separation between the existence of electron, for example, inside an atom. So there will be very nicely spaced electron levels. So there is a band gap, energy gap exists between two orbits. So electrons are confined in a discrete fashion at a very low temperatures. If I just increase the temperature, so electrons would fall into the continuous band. Okay, so you can see that connection of systems falling into the quantum regime or a classical regime depending on the temperature. That is the case, that is the why people are cooling all the quantum hardware to do the quantum computing, to have quantumness intact. Okay, for example, in this, let's say there is an atom which is having contributions coming from momentum in x, y, and z. There the kinetic energy would be 3 by 2 into kT. One example, this is a classical value. Okay, right? So I'm sorry, right? So classical harmonic oscillator in one dimension would have total energy is equal to mean energy is equal to kT. When it comes to quantum harmonic oscillator, we discussed this in detail today. Okay, specifically, right? For a quantum harmonic oscillator, the overall energy at a very, very low temperature, let's say t equal to 0, so energy would be half of h omega, that is a 0 point energy. This is what we discussed in the yesterday's session. Okay, so in today's session what we were going to do is we are going to talk in the perspective of the distribution of the system, statistical distribution. Okay, we have already now obtained what is the statistical distribution for a given system, right? So from that prospect, we'll try to see what is a classical harmonic oscillator, what is a quantum harmonic oscillator, and how they behave when the temperatures are varied from very low to very high. So that is the Gibbs statistical distribution of our Gibbs principle application to the oscillators. Okay, fine. So let me exit the screen here. Okay, so now, okay, yeah, this is lecture 1 and this is 2, session 2, and I want to go to session 3. Okay, right? So Gibbs principle. Okay, let me use my hand note. You can go through the content later. Okay, fine. Okay, yeah, if there is any questions, please do ask. Fundamentals of statistical and thermal physics. Superb, thank you. Yeah, okay. So the now question is, I was referring to let's say we need to apply Gibbs principle or statistical distribution to harmonic oscillator, whether it's a quantum or a classical. I said that. Okay, the question is why oscillator, quantum harmonic oscillator. Okay, so if I just take any system, for example, okay, for example, if I just take a solids consisting of atoms arranged in lattice. Okay, right? So arranged in lattice structure, right? They vibrate. Okay, lattice structures would do vibrations. like phonons, phononic vibrations. If I just go to within an electron, within an atom, electrons are oscillating, rotating. Okay, so which is called another oscillation, right? So you take any system in the universe, it is oscillating about its equilibrium state. It is simply equivalent to, if I just take a spring mass system, okay, which is vibrating about its equilibrium point. Very simple. Okay, so because of this reason, if you want to study things in detail which are vibrating about some point, so you use a harmonic oscillator formalism there. Okay, right? So why harmonic oscillator formalism? Answer is, you take any branch of science, there involves the system being displaced about its equilibrium point. When it let go, it will vibrate or oscillate or do some kind of a back and forth motion about those equilibrium point. So that is simply equal to the harmonic oscillator. Okay, so because of that, I would be needing to study that. So you keep it that aside. Now let's get back to the macroscopic, the microscopic and macroscopic systems which we are studying so far. Okay, for example, right, if I just take a system, okay, right, and which is existing at some temperature T, right, okay, and it is in thermal equilibrium. Okay, I have not disturbed it yet. It is in the equilibrium. Okay, system considered. Consider a system at T and in the equilibrium. In this case, there are so many things, so many microscopic systems. They can just do a rearrangement. For any given rearrangement, there is a corresponding energy. Okay, so how many rearrangements it can take, I don't know. Many rearrangements it can take depending on what is its internal structure. So let's say for R equal to 1, there is one rearrangement. The corresponding energy is E. Okay, R equal to 2, again it can get another rearrangement where the energy is ER or E2. Okay, I can just say E2, this is E1. Okay, if that kind of a rearrangement possibility is there, if I ask a question, what is the chance of system to exist in that particular energy state among all the possible arrangements? So that is simply given by PR. We derive this exponential minus beta ER divided by summation running over all possible arrangements exponential minus beta ER. So this is the statistical distribution of the system. Okay, it's a Gibbs distribution, or it's called a Gibbs principle. Gibbs principle, okay, or Gibbs distribution, right? Fine. Okay, so the denominator, we know that is a partition function, partition function, okay. Z is equal to exponential running over all R. Sometimes people write capital R also. Exponential minus beta ER. Okay. So just to get a flavor of what it is, what one can study is, let's consider PR for various values of T. Okay. Right. If you just take this expression, okay, right, let's assume that energies ERs, let's say they range between 0, 1, roughly 2, 3, 4, 5 and 6 so on, right, and you fix temperature T in the units of, right, K beta. Okay. So in that case, let's say temperature is fixed to 0.5. What happens? The probability, if I find probability expression, how it behaves is exponentially decaying. That is straightforward, right? I see that exponential decay. Okay, exponential decay probability. What it means is the lowest energy states, like which are very close, these lowest energy states are highly probable. Highly probable. Okay, but higher energy states are less probable. Okay. Now, just to see the effect of temperature, let me increase the temperature. Okay. If I just increase the temperature, what happens? Okay. So I just increase the temperature and just redo the plotting. What I'll get is, okay. So this would be correspond to T equal to, let's say, 5. What I see here is, in this particular case, okay, where lowest energy and highest energy are becoming very closely probable. Okay, so all the energy states become closely probable, means same, more or less same. Okay, so that is what the Gibbs distribution would tell me for a given temperature, for a given variation in the system rearrangement and the corresponding energies. Okay, right? So remember, this probability should sum to 1. Okay, that condition is also always there. So you can remember all PRs is equal to 1. If PR is discretely varying, if PR is varying continuously, okay, probability, in that case I can't have any more summation. I need to have a integration. Okay, so this is equal to 1, right, where energies run from 0 to infinity. Here in this case, the energies are corresponding to R varying, so energies would be discretely varying. Okay, right? So keep that aside. Now we know this distribution. Let me call it as a Gibbs distribution. Gibbs distribution, or you can say Gibbs principle of systems. Okay, fine. Now I want to, okay, let me show. I have a plot for various scenarios. Okay, see here. So this is for various temperatures. Okay, and I have it in my notes also. Let me show you. Okay, wait a minute. Yeah, fine. So please mind the values of probability. It is ranging from 2 here. It is ranging from 0.8 plus for temperature T of 0.5. It is, that is because the way I am going to substitute temperatures are in different units. Okay, right? So that need to be considered. So that's why there is a change in the like initial values of probability, but doesn't matter. The actual nature of the system is important. It is exponential decay. With the rise in the temperature, all the states of the system become equally probable. That is the case for T equal to 5 here in this case. Okay, I'm sorry. Let me get back to my notes. Right now, applying Gibbs principle to the harmonic oscillator. That is one of the objective for this particular syllabus. So we'll try to work on that. Okay. So like I said earlier, if I just take a simple pendulum, it is a harmonic oscillator, by the way. It has spring constant K0 and mass m. It can oscillate about its equilibrium point. Okay, when I disturb. Okay, so if I want to write energy of the system, harmonic oscillator, harmonic oscillator. Okay, you can say classical, right? So the hat comes in the hat for quantum harmonic oscillator. E comes with a E hat. Okay, so the energy of the total system would have kinetic energy plus potential energy of K0 x square, right? So you can also derive the K0 is actually m omega square, where omega is angular oscillation, angular frequency. Omega is angular velocity, I'm sorry, or angular frequency, you can say, right? Fine. So with that, energy becomes p square by 2m plus half into m omega square x square. Okay, let me increase the size of my pen. Yeah, fine. Okay, in this particular case, if I have a system of particles, all particles are there, each particle is approximated or treated to behave like, or treated to behave like a simple harmonic oscillator. In that case, what happens? Okay, right? As we know, there are so many particles, they can get rearranged and they exist with certain energy. Let's say that one rearrangement would have energy ER, and what is the chance of that system to exist in that particular energy? As we know, minus infinity to infinity E minus beta ER, right? So integration I am running here. Yeah, you know, earlier I was running the summation, now I am running the integration. That is because I am dropping the system into classical scenario. Okay, classical scenario where things are continuously varying. Fine. Okay, fine. So in this case, this is the energy. Now what I can simply do is substitute this energy here. Okay, so as I can see, E is a function of momentum and a position. Let me confine to only one direction, x direction, and momentum is also in one that direction. So in this case, what happens? Okay, so PR would be equal to exponential minus beta. What is explicit form of the energy you want to substitute? Okay, so that is p square by 2m plus m omega square, okay, x square by 2. Okay, right? So divided by, I'm sorry, that factor is also always there. Okay, the same factor running from minus, okay, I'm sorry, yeah, 0 to infinity exponential minus beta er der. Okay, right? So here in the denominator I have a energy er running from 0 to infinity. Okay, now as we know, the system is confined in a x coordinate and p coordinate. Like last class, in earlier classes, I was telling you there is a x coordinate, there is a position coordinate, momentum coordinate. I can divide that into small cells. Okay, and say system exists in one cell would allow me to find its future either by subtracting small volume element or small x element, p element from the old state to get the new state. Okay, right? So where the accuracy would depend on how small I take my dx and dp. Let me call that is something very close to the Planck's constant h. Okay, right? So the Planck's constant h, sorry, okay, this is small delta x delta p. Okay, now so here dx into dp is a volume element, any volume element, okay, any cell, right? So since this and these two are not same, delta x into delta p are not equal to delta x by delta p, so there may be many cells would exist, many such cells would exist in a small area element. So how many such things are existing? I just simply divide dx into dp by h. I would get the number of cells I have chosen. Okay, so that means the small energy is in the integration. Okay, right? So is equal to small dx by dp by h cat h. So you should remember how I am going to convert this into position and momentum integrals is by using this conversion factor. Okay, so that means the moment I do it, it becomes very simple. So z is the partition function is equal to, okay, integral of minus infinity to infinity minus infinity to infinity, okay, exponential minus beta p square by 2m plus m omega square x square by 2, okay, right, into dx dp divided by h. Very important. Okay, so I converted the integration in terms of energy, small energies, into small surface element obtained from position and momentum changes. Okay, right? So what happens now? I have a double integration. Okay, so let me expand systematically. H exponential minus b p square by 2m dp, okay, minus infinity to infinity integration minus b m omega square x square, okay, by 2 integration over dx. Okay, so if you carefully see, this is a Gaussian integration, the Gaussian integral, this is the Gaussian integral, two Gaussian integrals. Okay, so it's worth to find how the Gaussian integration is done. Okay, so if I had to generalize both the integrals into one form, that would be minus infinity, these are looks like exponential minus alpha square z square dz. Okay, so looks like, right? So what I'll do, I just introduce alpha z equal to x lit. In that case, alpha dz is equal to dx, right? Dz is equal to dx by alpha. Okay, right? So limits are not going to change because I'm just taking just a scaled version of z in terms of x. So limits would remain the same. So this integral would convert into minus infinity to infinity 1 over alpha exponential minus x square dx. It becomes simple. Okay, so please don't get confused with this x and this x. Okay, right? So now this is just a generic Gaussian integral. Now I want to find what is this, or you can just find what is this. Okay, so I want to find minus integration infinity to into dx. This I want to find. let me call some capital I. It's not easy. Okay, so what I can do, let me square this. Let me take a square of this. So since it is integration of particular variable, I would use some dummy variables to ensure it is proper. Minus y square dx, sorry, dy. Fine. Okay, if this would look like minus infinity to infinity, minus infinity to infinity, e to the power of x square plus y square dx dy. Okay, so what you see here, what is this factor, is actually if r equal to xi plus yj and x is equal to r cos theta, y equal to r sin theta in polar coordinate system. Okay, so r square would be x square plus y square. Okay, right? So dx dy is a small surface element, right? The surface element. What surface element is this? If I just take a coordinate system, okay, if this is x, this is y, small change in x, small change in y, it creates a surface element. So this is dx dy. Okay, if I integrate from x from 0 minus infinity to infinity, y from minus infinity, I'll get overall surface. Okay, right? So same thing I can also do if I just take a polar coordinate vector in terms of polar coordinate r. Let's say vector r makes a theta. Okay, now small change in r, let me take dr, and let's say increase theta by small angle d theta. Okay, so small change in dr, small angle change multiplied by d theta into r is the arc length. Arc length multiplied by dr would create a surface element. Okay, now you see, instead of running x and y to minus infinity to infinity to cover the entire surface, for integration, what I can do, I can run r from 0 to infinity and theta from 0 to 2 pi. If I do that, I also cover the same thing. So it's easier in this fashion. So my integration I square integral becomes 0 to infinity, 0 to 2 pi, exponential minus r square. Okay, dx dy is equal to r dr d theta. Okay, so let me substitute that r dr d theta. Okay, so theta doesn't depend on anything, so straight away the integration of 0 to 2 pi d theta would give you 2 pi, and what is left is integration of 0 to infinity r exponential minus r square dr r dr. If I just put r square equal to t, 2r dr is dt, r dr is dt by 2. So let's substitute here 1 over 2 x 0 to infinity minus t dt. Okay, so this would be 1 over t exponential minus t divided by, okay, minus this would be minus 1 integration. Okay, and you run 0 to infinity. So what you get here is, okay, what you get here is this is equal to 1. Okay, right? That means I square I'll get pi. Okay, so that means pi the integrand is square root of pi. So that is what I got. Okay, so let me get back. So this is going to be square root of pi. If this is square root of pi, okay, so what is the a factor? What is this factor? Okay, so interestingly, okay, so interestingly, integration from minus infinity to infinity, exponential minus alpha square z square dz is simply square root of pi by alpha. But in our case, what I have, minus infinity to infinity exponential minus beta p square by 2m into dp into dx. Okay, this is I have. So in place of alpha, what I have? In place of alpha square, I have beta by 2m. So alpha is square root of beta by 2m. So I have to substitute that. So integrand is square root of pi divided by b into 2m. Okay. But in the case of another integrand, exponential minus, sorry, exponential minus beta into m omega square x square by 2 dx dp. Okay, in this situation, in place of alpha, what I have? Alpha square I have beta m omega square by 2 I have. So this integrand would be square root of pi by beta m omega square into 2. So which is 2 pi by beta m omega square. Okay, right? So now I want to find what is the overall energy, right? Average energy E, which is 1 over h, both the integrands. So first integrand is square root of 2 pi m by beta multiplied by square root of 2 pi b m omega square. Okay, so m gets cancels. Okay, so it would be equal to 2 pi beta h into omega. H by 2 pi is h cut, so this would be beta is 1 over k beta, so I'll have h omega. So overall energy I got is equal to thermal energy divided by, sorry, so this is not the energy, this is I'm sorry, this is a partition function. Okay, so partition function is h omega. The next stage is I can find the overall, mean energy. So mean energy, as you know, mean energy is equal to minus derivative of ln z. Okay, right? So by the way, what is ln, what is z? Z is 2 pi by h beta omega. Okay, so ln z would be minus d beta 2 pi by h beta omega. Okay, so ln, which is equal to minus dou by dou beta log 2 pi minus log h minus log beta minus log omega. Okay, so this is constant with beta, this is constant with beta, this is constant with beta. They are not going to contribute. Only this is the term which is going to contribute. So which is equal to minus of minus plus derivative of b, like a log of beta with beta derivative. So which is 1 over beta. Okay, so 1 over beta. So I did miss minus sign somewhere. Yeah, I think so. A minus sign here. Okay, so that minus sign would be taken care somewhere inside. Okay, so I'll get a minus 1 over k beta. Okay, so that minus takes care. So average energy I can write either way is 1 over beta, so that will become K beta, Boltzmann constant. Okay, so this is in general quadratic term existing energy contributions. Each contributes half K beta, another contributes half K beta. So if I had to explicitly write down P square by 2m, P square by 2m plus half m omega square x square, this contributes half K beta, this contributes half K beta for the average energy. So overall is this. Okay, so simple harmonic oscillator average energy, simple harmonic oscillator average energy is just K beta as per Gibbs principle or Gibbs distribution. Okay, now I want to work in terms of quantumness, quantum harmonic oscillator. Okay, so quantum harmonic oscillator. Okay, so again the energy. Okay, let me write down quantum harmonic oscillator. Okay, right. So is there a, okay, the Reef has another book on statistical mechanics which is part of Berkeley Optics volume 5. I think you can use either book, both would consist. I hope that literature works as a reference to our course. Yeah, right. Okay, so both books are good. Yeah, so I did not find the hard copy, soft copy available of this this book, volume 5, statistical mechanics, which is a part of Berkeley physics course. Okay, so I am using currently the other one, the fundamentals of statistical and thermal physics. Both are more or less the terminology, everything is same. Okay, I would feel the statistical mechanics book would be much more simpler. Okay, because I referred long back, but I don't remember. Okay, for harmonic oscillator, we just use the same energy expression. Okay, only difference here would be, okay, my god, this is happening again. Fine. So only difference is position and momentums. Okay, position momentums would be slightly different. They become operators. Energy becomes energy operator. Okay. Okay, let me refresh. Yes, thank God. So quantum is hat, a hat. Okay, that's the difference. Okay, so momentum, let's say momentum operator would be minus IH cross dou by dou x, operator form, the operator forms. Okay, very important, it's a part of quantum physics. Okay, if somebody wants how it is derived, I can refer to my notes. Okay, it's very simple, it is easily derivable. Okay, right. So energy operator IH cross dou by dou t. Okay, for time being we don't use right now. We need this one, and position operator is simply multiplying position. Okay, so a p onto a wave function is, if wave function is dependent on x, so which is equal to minus IH cross dou by dou x psi of x. Okay, I hope this is covered, right? So let's say if p is acted on some constant value, so that would be minus IH cross dou by dou x into 1, which gives me 0. Okay, remember, that is the thing. Now if I have P is like that, P square would be minus IH cross dou square by dou X square. Okay, that is the thing. Now, as we know, for a harmonic oscillator, okay, the energies are E, can exist with quantum states, quantum wave functions, and it has some Hamiltonian, which is H. So this is a eigenvalue equation. So let me put hats, and this is a, let's say, a function dependent on X and P. For simplicity, I'll just take X. Okay, right? X and P. Okay, let me put that also. Okay, so here if I see H explicitly in terms of kinetic energy plus potential energy, okay, and put that inside, so because of this it becomes a second order differential equation. Okay, it's not easy to solve second order differential equations, so what people use some algebraic method, okay, and they can get exactly what kind of a states system would exist in, okay, with what energy system would exist in. Interestingly, because of the quantumness, system bound to exist in certain discrete states, let's say n equal to 0, n equal to 1, n equal to 2, n equal to 3, n equal to 4. You see, deliberately I'm decreasing the space between two orbits. So which is simply like I have a nucleus here, okay, something like that. Okay, fine. So in this case, if I solve the Schrodinger equation, okay, right? Algebraically, remember, algebraically, not literally solving, algebraically, then what you can get is there exist the energy states En is equal to n plus half into h cut omega. Okay, and orbits are like ground state. Orbits would be psi of 0 would be ground, psi of 1 would be excited, okay, excited, psi of 2 is second excited, and so on and so on. Okay, right? So what important for me or for us right now is the energy. Okay, n plus half into h omega. This is matters for me. Why it matters for me is my partition function is a function summation over r beta er. Okay, right? So let's try to find out what is the partition function. What is the partition function for given En? Okay, right? So let's try to find it out. So since the things are discrete, see, things are discrete, so I have to use a partition function in terms of summation only, where n range from 0 to infinity. Remember how I am changing. So here number of states, various possible states. Here the like systems existing in 0 state, 1 state, and so on. Both are same, just counting only, so saying in different fashion, so which is equal to minus beta into En. Okay, let me write explicitly what is exponential beta n plus half h omega. Fine. So this has got two terms here, n infinity exponential beta n h omega exponential h beta h omega by 2. So this is the thing which can come out, right? So what is left is this factor, e beta h omega. Let me write down that as n. Okay. So if you carefully see, e to the power of beta h omega, right? Okay. So beta h omega is what? H omega by kt. Okay. So this would be for equal thermal energy and equal system energy, right? Electromagnetic energy, which is close to 1. So in that case, the summation over, so in that case, this would act like just some function x, some value x, which is close to 1. Okay. So that means I'll have x to the power of n, which is the summation. Actually, you can prove that it is equal to 1 over x, 1 over 1 minus x. So this is equal to 1 by 1 minus exponential minus beta h cut omega. Okay. So by the way, I got the summation. Now what is my z? So z is this factor, okay, sorry, this factor multiplied by this. So z would be exponential minus beta h omega by 2 multiplied by 1 minus beta h omega, which would be 1 over, okay, exponential plus beta h omega by 2 minus beta h omega minus by 2. Okay. So I got nice expression. There is a long z if I want to find, which would be, okay. Uh, okay. So yeah. So which would be what? Minus, right, log of exponential beta h omega by 2 minus I'm sorry, log 1 minus beta h omega. Okay, right? So I have explicitly writing down previous situation. So what you will get here is minus half, okay, overall minus, right? Sorry, this is yeah, yeah, right. So what I'll have here is the h omega minus 1 by 1 minus, if I just integrate, so differentiate with a d by deta with a minus sign. Okay. So what I'll get is e to the power of minus beta h omega multiplied by minus beta h omega minus h omega. Okay. So if I simplify this entire thing, we'll get h omega by 2 plus exponential minus beta h omega divided by 1 minus beta h omega into h omega. Again, I can take the common 1 by 2, 1 by 2 plus 1 over e beta h omega minus 1. Okay. So the average energy is this. Now the things. So this is for quantum simple harmonic oscillator. Okay. Now let's say take the case where t is tending to 0, very low values. In that case, beta h omega is h omega by k beta t. This would tend to what? Infinity. Okay. So if this tend to infinity, exponential infinity would tend to infinity. 1 over exponential infinity would tend to 0. So second term is not going to contribute. Average energy is simply h omega by 2. That is a 0-point energy. Even the temperature is 0, the quantum harmonic oscillator bound to exist in some energy. Okay, the Gibbs principle would tells that. Okay, so Gibbs distribution or principle implies 0-point energy. Now let's take for a very large t tends to infinity. Okay, so t tends to infinity case, beta h omega, what it will tend to 0, means exponential e to the power of exponential tend to 1. Okay, so 1 by 1 minus 1 would tends to what, 1 by 0, so which tends to infinity. So that means the factor of 1 by e beta h omega minus 1 would be much larger than half. Okay, so that means I can just simply take average energy would be h omega multiplied by, neglect the half. Okay, neglect the half part and just take only 1 by e beta h omega. Okay, so now this I have. So e beta h omega I can approximate as 1 plus beta h omega and so many higher order terms. So there is a minus sign. So there is a minus 1. Okay, let me refresh. Okay, 1 minute, guys. Do I have today's which is today's? Yeah. Okay, right? So minus sign, minus sign. So minus 1 would be minus 1. You can neglect the higher order terms which are diminishing anyway. So I'll get which is equal to beta h omega. So which means average energy would be h omega 1 by beta h omega. H omega cancels. So I'll get k beta t. Okay. So you see, when the temperature goes high, as classical systems, as you say, as go, even quantum systems tend towards classical limit. Okay, so this is the kBt classical value. Okay, fine. So we just got that now earlier. Here you see. 1 minute. Yeah, here. This is a simple harmonic oscillator. So now we applied Gibbs principle for both simple harmonic oscillator and classical quantum harmonic oscillator. Both the cases we applied and we saw what would be the scenarios. The most important part is temperature. That is the key. Even you take a quantum systems, if you try to increase the temperature, the quantum system no more exists in quantum form. It goes everywhere. Okay. So if I just take quantum system, let's say ground state, one state, if it is 2 and 3 and are also available for that, so usually what I want to create a quantum state alpha 0 plus beta 1 in superposition. Okay, I am writing in Dirac notation here, in Dirac. So far I have not done. I'm just trying to connect what is discussed to the quantum computing. Okay, now I cool the temperature so that the system electron would exist between 0 and 1 with some probability. So it is actually hopping between 0 and 1. So it is called, it does the Rabi oscillations. That is a part of being superposition. Superposition. Okay, right? Okay, so if there is no chance for the electron to go beyond this excited state 1, it will stay there. If I raise the temperature, rise. In that case, what happens? The temperature around would create a thermal energy. Rise would give leads to thermal energy. Okay. Now the energy separation, this energy separation is delta E. Okay, the band gap, let's say. If rise in temperature leads to larger than delta E, electron would immediately, instead of being in superposition, it goes somewhere else, means it will try to go to level 2. Okay, if the temperature is slightly increased. If the temperature is much larger, it would also go to level 3. Okay, if the temperature is very, very large, and the electron may completely go out of the atom. Okay, for very large T, electron may go out of the atom. So that would lead me to, so in result, no superposition. Okay, so that is very important. So the statistical physics, the Gibbs distribution would tell me the need for reducing the temperatures of the system even systematically. Okay, now I have, let me show you. Okay, I'm sorry. For a classical versus quantum harmonic oscillator plots I have here. Here you see mean energy versus temperature of the classical and quantum harmonic oscillator. If you carefully see, the dotted blue color is a classical harmonic oscillator. With rise in temperature, I don't see anything, because in a classical case, I don't bother. So there are so many atoms exist, rise in the temperature, the mean energy would rise. It's a linear. Okay. But when it comes to quantum, it is not linear when it comes to lower temperatures. You see, very, very important. Okay. So at very lower temperature case, it is slowly not increasing, and then it increases. It shows a nicer kind of a small parabolic behavior, quadratic behavior. Okay, right? Not exactly quadratic, but it's slightly like that. Okay, so that is a literal comparison between classical to quantum harmonic oscillator when Gibbs principle or statistical distribution is applied to them to know the average energy. Average energy is the key. Like if I talk anything, let's say if the class students have performed well, means immediate next question would ask what is the average, right? For any system, if you take, the average is the key. So that's what we want to find and see how average changes with respect to different parameters. Okay, fine. So right now we have what we have 40 minutes more. If there is any question, please do ask. Let me see. But how 1 by r potential of nucleus can be modeled as harmonic oscillator? Okay, potential of a nucleus. Okay. What I mean by 1 by r, I'm not getting. See, basically, for example, nucleus case we are talking about, or atomic case you are talking about. Okay, there is a nucleus, there is an electron revolving around. What is the energy of the electron? Okay, that is what harmonic oscillator, quantum harmonic oscillator. So now you are talking in terms of, I think, central potential, I guess, central potential. Okay, so even there, I think you can bring in harmonic oscillator, something which is vibrating, and we'll bring that. Okay, so I don't think there is a connection of your question to the harmonic oscillator. Okay, fine. Okay, so the next thing is, let's see not only the energy. See, z, if I just take a partition function, okay, So just take, it gives me the method to calculate, easiest method to calculate average energy. How? Average energy is simply derivative of ln z. Okay, ln z. Very simple. I don't need to know anything. I just find the partition function, which is, if it is a quantum system, I will count the number of available accessible states. Okay, and then find log of that partition function and then differentiate it. If the system is classical, in that case, I would be running, okay, integration e to the power of minus beta er der, where energy may run from minus infinity to infinity. Again, there also I would find what is the average energy. Okay, so that is a power of partition function. Not only that particular average energy, partition function could also give a method to find the mean gas energy. Why I'm bringing the gas is collection of atoms, okay, atoms which are separated to a far places is actually called a gas. Okay, and Z also could give the entropy. We saw like last time, na? Yesterday's class. And yes, Z also can give the energy dispersion, average energy dispersion, mean energy dispersion. What I mean is, if the mean is existing somewhere, okay, E equal to E bar, or so there is a distribution of energy delta E. Okay, how these things are distributed within this, the systems are, I can find from there. Okay, so that is the power of partition function. Okay, right? So what one can do is, one can start with the microscopic system and put all together and make a macroscopic. So the information of microscopic put together could give macroscopic information. Okay, right? So the connection is, I just take, let's say, for example, in the case of IBM computers, okay, there they have qubits, Q1, Q2, Q3, Q4, Q5, that like transpond LCR based circuits actually. Let's say all the qubits were connected. Okay, it's called a 5-qubit architecture. Okay, now to study this macroscopically, what I'll do, I'll start describing each individual microscopically and put them together. Probably I'll come up with the macroscopic, and the partition function I will get z e to the power of minus beta er, and from there I'll calculate whatever I want. Okay, right? So now the question is, let's say if the systems are system with the particles not interacting. Okay, okay, in that case what happens? Not interacting. In that case what happens? It becomes very easy to find the partition function. The moment you have a partition function, you can calculate everything. Okay, wait a minute. Okay, system with a partition, system with particles not interacting. Okay, finding Z is very easy. Okay, let's say if the system is having interacting particles like here. Okay, so it would be difficult. I'll not say difficult. It would be tedious compared to non-interacting case, but doable, not impossible. Okay, right? So that is what people can do. Okay, for a classical situation, usually what people does, just define a quantum state, define, for example, if I want to find average energy, classically, to find average energy, what they'll do, people start with what is the energy, let's say energy of the system located at some coordinate, position coordinate, momentum coordinate. They start, and then from there they'll count all of them and find the partition function. Okay, if the energies are varying continuously, in that case it would be integration. Okay, so classical scenario would fall to integration, right? So we already saw that. Okay, for the system, for example, let me take a new notebook. Okay, let me take a new notebook. Yes. Okay, yeah. Okay, so the partition function having so many coordinates would be various integrals, okay, where each integral would be q1 to qn, okay, p1 to pn, right, and dq, dq2, so on, dqn, dp1 to dpn. Remember, divided by small h naught volume element, which is in the dimensions of n. Okay, it's not power. Maybe in the notes I might have mentioned as a n, so it's not a power. Okay, so if I want to find, let's say, the entropy, okay, what I'll do, I just say the system, let's say, initially existing in this energy ER, okay, right, it gets added E naught from the external means, okay. Initially there is a partition function, initial Z with energy ER, okay. So when external means added, so it will become ER star, okay. In this case even Z also changes, which would be, here Z is just exponential minus beta ER, here Z would be exponential minus beta ER plus a small E naught, small energy. So I'm talking about the external intervention, how it can be studied using the partition function, simple partition function. Okay, so Z star is simply equal to, if you carefully see, E minus beta epsilon naught minus ER, which is E to the power of minus beta epsilon naught, just a simple Z. Okay, so let's take a log of the entire thing, which is log Z minus beta epsilon naught. So what it says is log of the new partition function when the energy is added is equal to log of old partition function minus beta epsilon naught. So the new energy average mean energy would be equal to minus dou by dou b ln z star, which is, carefully see, ln old z divided by d beta dou by dou beta minus epsilon naught, minus of minus becomes plus. So which is average energy of the old system plus some E naught. So what it conveying for me is, when I add a mean and some energy to the system, the mean energy of the system also changes. So which I derived, the partition function gives the idea that mean energy would increase by E naught if the E naught energy is added to the system. Okay, very simple, right? So usually where that energy goes and where it is occupied, okay, whether it is given to particular atom, all those things I don't bother. Using partition function, I'll just get the mean energy. Okay, right? And one more thing, as you guys know, the entropy of the system, entropy, if I just find entropy is formula Boltzmann constant log z plus beta into average energy. Now, when the energy is added, so new entropy is coming, which is equal to minus k log of new partition function plus new average energy. This is a formula. Okay, right? So now let me substitute what is log of z. Log of z is what? Z star is log of z minus beta epsilon naught plus what is the average mean energy of the new system, which would be simple addition of old system plus beta epsilon naught. You see, this gets cancels, minus k log z plus beta average. So what it's saying is entropy remains the same even if we add the energy. Okay, so any quantity inducing, like any quantity would not change the log side by adding some quantity, energy quantity, but entropy wise there will be no change, but the rearrangement would take place provided the small energy is added. Okay, right? Now again, what would be the entropy of the system if I add an extra system to that? Let's say initially I have system A prime, I add another A double prime, I create a A. Okay, right? Let's say this exists with energy ER, this exists with energy ES. Okay, let me call primes. Okay, so overall energy is, let's say, ERS. Now in that case, what would be the entropy? Okay, for example, this is helium atoms, this is neon. Okay, right? So let's say that, yeah, nitrogen, I'm sorry. Okay, so let's say what is the partition function for this combined system would be partition function of system A plus this partition sorry, wait a minute, partition function of system B, simple product. So which would become partition function minus B ER plus ES. So that is the overall energy, ERS. Okay, so that we know overall energy is ER plus ES. Okay, so what it says is that would be simple product of two systems, and their ln z is also ln z prime plus ln z double prime. Okay, so the partition function gives a technique, a trick to even find a combined system, the factors, physical features. So the combined systems physical features could be easily found using z of combined system. Okay, so that is what the power of a partition function. Okay, right now let's get back talking in terms of combined system, right? Let's get back, or let's say I have a many body system. Okay, so many body systems means, let's say I have so many body system, very very important. Okay, right, for quantum physics is quantum computing is very very important. So for a many body system, each atom, or let's say each qubit, could be treated as harmonic oscillator. Let's say it is located some, let's say each system has position Ri, a momentum Pi. Okay, right? Fine. So energy would be what? Right? So each one, let me write down each one's Pi square by 2m plus potential energy of that system located at some R1. So if I have to write down for all the systems, I would run from I, let's say 1 to n of n particles. Okay, 1 to n. n. Okay, now R2 and so R. Why this is happening? Yes. So this this is kinetic energy, this potential energy. Okay, so let's say ideal gas situation means all the particles are far far away. Ideal gas approximation means no interaction. As if one atom doesn't see the other atom, or one particle doesn't see the other particle. So in that case, usually U, which refers to the interaction, okay, U refers to the interaction, U would become 0. Okay, right? So I'll have Z is simply equal to exponential minus beta P1 square plus P2 square, I'm sorry, P3 square, okay, so on. Okay, I need to put 2m everywhere up to Pn square by 2m, right? And the integration should run what? Small dr1, small dr2 up to drn. Remember, it's a volumetric integration because I'm talking in terms of, let's say, dimension, 3-dimension. For example, for the 3-dimension, R would be xi plus yj plus zk. Okay, and similarly, position vectors, momentum vectors. Okay, which is px, pxi plus pyj, pyj. Okay, and then pzk. Fine. Okay, there is a question on superposition state. We'll come to that point. Okay, so in the last 10 minutes, I will touch on that. Okay, right? So this is plus PZK, right? So now this entire volume element dp dp2 and so on dpn divided by h, remember that should be there. So three-dimensional coordinate system, h cube, how many atoms are there? There are n atoms. So just to avoid the confusion, we'll put that. Okay, so z, if I just get, what I'll have is 1 over h3n. I'll have integrals, each are depending on quadratic terms. How many? There are n's. Okay, so you can simply get what is the contribution coming from each term. Okay, we already got it earlier, so from there you can apply. Okay, so what you get exactly is a Gaussian integration you will get. So z would be simply equal to, okay, 1 by h3n, okay, square root of pi by beta 2m. Remember, so for three coordinates px, py, pz, right? Okay, and now I wanted to bring certain volume into the picture. If the system is confined in a volume V, so that will become here V, right? Okay, so literally if I had to find for this system, it would be V into 2 pi by m beta h square by 3 by 2. Okay, right? So if I'm talking about all the atoms, so I'll have n here. Okay, it's just a product. Now, depending what is this implies? Implies average energy of the global system would be simply n times average energy of the individuals. Okay, right? Okay. Now, talking about the togetherness, combining the systems. Okay, so if you carefully see, if I just take, let's say systems are separated. Let's say there is a system with the n particles confined in a volume V, that is at temperature T. Okay, right? So another partition, again same number of particles, n, and temperature is T. So I have a partition. Okay, now if the particles are distinguishable, okay, classically, right? And then let's say if I remove the partition is removed. In that case, all particles would go back and forth. Okay, so in that case, I'll get some S entropy. Here, let me call this is S1 entropy. This is S2 entropy. Okay, when I remove partition, I'll get S1 plus S2, and here I'll have overall ST. Okay, so interestingly, if I confine that particles are distinguishable, okay, and they can move around, and if I try to see, in that case, these two things sometimes appear to be not equal. Okay, right? That is not the case, because like when the things are like at the quantum level or at the atomic level, we can't say that things can be distinguishable. So things has to be indistinguishable. The moment you bring in that idea of indistinguishability, so then even this gets equal. Okay, this is taken care. So it is called Gibbs paradox. Okay, Gibbs paradox says the entropy do not get added up correctly. Okay, sometimes Gibbs. So when correctly, this is because of our perception of seeing things distinguishable, or question of seeing particles as distinguishable or indistinguishable. Okay, right? So because of that, this paradox would appear. So one problem is, when I remove the partition, you see, this particle can go anywhere, na? So the entropy I should calculate for the S1 should calculate with the 2V, and even S2 should be calculated with the 2V. But what I do, I just calculate for, even after removing the partition, calculate for the with V, and this is with the V, and when I add them, it leads to problem. But if I calculate S for overall volume, S1 for overall volume, S2 for overall volume, and then when I add, this Gibbs paradox would be eliminated. If the S1 is calculated for 2V when partition is removed. Okay, same story for S2 also. In that case, S1 plus S2 would become S total, right? Here I was saying S1 plus S2 is not equal to ST, right? So that would be eliminated by if you just take a assume that the particles, when I remove the partition, doesn't mean they're equal in number, confined to same volume, they'll not move around. If I assume it, it's a classical way of seeing things. Okay, quantum mechanically what happens, particles are not confined to a location, so they move around. So that picture is taken, or a formalism is taken, I'll just get the right results. The paradoxes are removed. Okay, fine. So in the notes, I have a literal description of this Gibbs paradox. Okay, right here. Here I have. You can go through mathematics. Okay, I've discussed that. Fine. Let's come back. Last 10 minutes. Let's come back and see some questions. So can you please tell us a little bit more about how superposition states is achieved? What is n? What is h to the power of 3n? Okay. Okay. So let's come from the back. Okay. What is n? Okay. So let me use my hand notes. That is easier. Where do I start n? Yes. Okay. So this is where. So for a many body system means I'm talking about so many different number of particles. So n is the total number of particles. That means the I index runs between 1 to n. Okay. Now, one more question you have asked is, why h to the power of cube to the power of n? Okay. So in the case of partition function, if you say C, okay, where did I, yeah, here. Okay. So here in the denominator, I'm adding h naught. H naught is a small volume element divided to the power of 3n. So why is this so? Maybe I will explain using that. Okay. For example, I have a coordinate system Q and P. Several times I told, but anyway, I will do it again to better understanding. Okay. So things are divided now. Okay. So I'll just go to such a small level. If I want to find P final, okay, so I'll take P initial, I'll add small dp. Q final, Q initial plus small dq. Okay, right? Let's say system is here initially. So I want to find where it is a new location. This is old, this is new. What I'll do, I'll just add, right? Okay, so the initial system is located in this particular volume element, surface volume. This is called surface element. Okay, where it is located? It is located d. It is located. Just a minute. Where is this old one located? Located at this x-axis. This y-axis is this. Okay. Now, for a better accuracy, what I will do, I just divide this entire p coordinate and q coordinate so small, right? So small that delta q into delta p could be close to h, Planck's constant. Okay. So why close to Planck's constant is, as you know, entropy cannot be less, sorry, uncertainty cannot be less than Planck's constant. Okay, so that I take in here, I'll just take a volume element so small is equal to h. Okay, so in my coordinate system, the surface element is divided into such a small units. Now the question is, my integration is dp and dq. Okay, right? So what is this dp dq is? Z usually comes with exponential minus beta er der. Okay, varying in small energy element, how many number of particles exist in that particular small energy range when E runs between E to E plus delta ER, na? Right? How many exist in this small window? I want to find. Those things would come from the partition function. It's like basically counting. Okay, so for that, what I'll do, I'll just change small dr and just count, and this another small dr I just count. Okay, so in that way I'm just counting. Let's say this dr is ranging from minus infinity to infinity. I'll have the system which is ranges from energies range from minus infinity to infinity. The same thing I just convert into this another integral where b e is a function of p and function of q, where this is converted into, so this is what? This is a energies element, small energy element. If I want to convert that to small, this one, what I have to do? I have to divide it by h naught or h, simply h. Okay, so that is what dp by dq by h. It is just a 2 degree of freedom I'm just talking about. Let's say qa is having qx, qy, qz. P is having px, py, pz. In that case, what happens? I need to have dpx, dpy, dpz, dqx, dqy, okay, dqz, right? Okay, so this entire thing is h. Remember, this h and this h is slightly different. This is a surface element, this is a three-dimensional surface element. So just to show the difference between this to this, I'll just put a 3 there. Okay, right? Now I have n such particles. So this n, for n particles means I'll have, this is dude. Okay, instead of 3, just like this. What I mean is 3n means I have a element made out of dp 1x, dp 1y, dp 1z, okay, dq 1x, dq 1y, dq 1z, and this is just for one, and there are so many like that. there is a dp2 and so on. Okay, how many are there? That will create a small higher dimensional surface element. Okay, surface element, right? So how many number of delta p1x, delta p1y, delta q1z, how many within this small element, how many such small elements are there? How many small elements are there? Okay, so this is the large element. Okay, for the integral it is coming out for the integral, but my intention was to divide the entire surface element to so small I would come and fall the calculation, bring the calculation in the uncertainty, maximum uncertainty, less uncertainty means maximum accuracy range, uncertainty principle. So that is why I'll have this entire thing is divided by h naught 3n. It is not a power. H naught 3n stands for, it is of area of the element calculated with the 3n variables. That is what I have. Okay, right? So I think it is explicitly written. Where do I have? Wait a minute. Yeah, it is somewhere, I think. Yeah. Okay. Yeah. Where did I write that? Yeah, here. Okay, for specific scenario, you have h naught to the power of 3. 3 stands for 3-dimensional. 3n stands for 3n dimensional. It's not a power, remember. Okay, right. And one thing, remember, I think I have given you already here. Conversion between small change in ER to small change in two coordinates of P and Q comes with the denominator. Okay, fine. Okay, so quick last question we'll go to. Can you please tell more about how superposition state is achieved? Very good. Okay, so how, let's say I cool the system to too low temperature. Okay, right? So what happens in that case? 1 minute.
Sir, I think you're not audible. Hello.
Thanks for noting. Thank
Yeah.
you. Yeah, yeah. Okay. So initially, let's say system is cooled down to this state. Okay. Now, as per quantum computing, you might have come across when you act a Hadamard gate, Hadamard, onto quantum state, so which is gives you a superposition, equal superposition is like this. Okay, what I mean is 50% of the time the electron would be here, 50% of the time electron would be here. So 50% probability, 50% probability, Hadamard gate. Okay, when it happens, okay, so when it happens means it has to exist here, here 50% means it is fluctuating between here and there. Okay, it is just like a quantum coin. Okay, right, it is a quantum coin. So why I'm saying quantum coin means you just take a classical coin, what I have a currency coin. If you just take, if you flip, you will have heads 50% chance, tails 50% chance, probability. Okay, so what it is doing, let's say I flip a coin. Okay, when I flip a coin, it is actually in a superposition of head and tail superposition. Okay, so what I have to do to put the things in superposition, I have to give the energy. So you give a flip energy. Okay, flip energy, coin flip, right? So in that way, it is actually existing in both head and tail, head and tail, head and tail. So same thing here. If I just supply energy to the atom which is in the ground, if I supply energy in the form of some photon, usually it goes to high state and then comes back. It has some lifetime, comes back. By the time it comes back, I send one more photon. So what I'll do, I'll take a pulse of photons. There are so many photons in it, nicely placed. If I send that to atom, so what atom does is it takes the electron or photon and send the electron to the up and down, up and down, up and down. It does the oscillation. So if I have to write that in the form of some mathematical formula, which would be superposition of 0 plus 1 divided by square root of 2, where the pulse which is coming here correspond to Hadamard gate. Okay, right? Probably it might have been introduced to you. Initially, the quantum state is in 0, means in the Bloch sphere, if you just see, okay, it is pointing towards, psi is pointing towards the north pole. When I try to rotate that vector, quantum vector towards the x direction, okay, what happens? I'll have superposition of x plus 1, sorry, 0 plus 1 divided by 2. So basically, Hadamard gate does the quantum state vector transition by pi by 2. So it is also called area of the pulse is also pi by 2. Okay, so this is how mathematically described how superposition states are achieved. Okay, the simplest example, how it is done in the lab is they take atoms. Okay, so atoms means, let's say there is a ground state, there is a excited state. Let's say electron is here. So they send a bunch of photons, laser light. So electrons would go back and forth. It's very, very small time, remember. So that is what the coherence time, decoherence people call. So within that time, they may say there is a superposition existing. Okay, so this is what superposition is mean. Okay, for example, this is the electron case. Let's say I have a photon, means energy. So let's say I have a mirrors. Okay, mirrors. If I send a light, means I send one single photon and just slightly arranged in such a way that photon goes back and forth continuously, right? So now a photon is going back and forth. It creates a standing wave pattern, like it can have a standing wave pattern like this. It can have standing wave pattern like this. So why it can have multiple standing wave patterns? Because it is quantum in nature. So quantum means probabilistic. Okay, probabilistic. That means photon can exist in this state. Let me call this is a state 1, this is in state 2. So the two superposition of two states. For a photonic case, it is slightly different. For a photonic case, what they will say, the number of photons existing in particular state is called a Fock state or coherent states. So superposition is created between two coherent states or two Fock states. Like that, superposition is achieved. Okay. Yeah. Do the photons need to be coherent? It's not. I think two photons, the moment you taken off from lasers, probably you can separate them in such a way that you can create entanglement and use computing. So coherence is not mandatory, but if you have, it's good. Okay, talking in the particular context, whichever context you are talking about. Okay, fine. So that's about for today. If there are any more questions, what will be the case for entanglement? Yeah. For the entanglement, people take a coherent light source only, that is a laser source only. Laser source they take. They use something called non-linear crystals. Non-linear crystals. Okay. They use something called photonic down conversion. Okay. Right. A spontaneous photonic down conversion. And let's say there is 100 joules, one photon is coming. I would get two photons of 50 joule and 50 joule. So these two photons are entangled. Okay. Right. So the way we entangle two atoms, two qubits, Q1, Q2, we can entangle and separate them. Okay. And does something with this would have some effect on this. The same way, if you just take a non-linear crystal, which depends on higher order susceptibilities, if you just take a non-linear crystal, send the coherent light through, you would get entangled photons. Okay. Right. So again, it's another in-depth study one has to do, how single photons are used to do the entanglement creation, all those things. Probably if I have some time, probably I'll touch tomorrow somewhere. I can give us some reference. Okay. So I'll stop here. I have one more meeting now. I'm sorry. Okay. I'll take the questions tomorrow. We have plenty of time tomorrow. Okay. Right. I'll upload today's notes as well as tomorrow session. Notes also I'll upload. You please go through the tomorrow session notes. It is again little bit mathematic and not little bit too much. Okay. Right. So, but like idea of this entire FDP is to equip faculty with the rigorous maths. Okay. So it is not just information. You are going to understand exactly what needs to be equipped with to teach the students. So that's why I put all the mathematics. Okay. My notes will cover everything. Please go through and read through it. Okay. So if somebody have found that book, okay, so please do share. Okay. Right. Okay then. Thank you so much.
Yeah, Maipal sir, please continue. Maipal sir, I think you're on mute.
Thank you so much, sir. It was a